Hey guys, as I mentioned in my message to you, the audio for this did not record, so I'm voicing over this on my phone. This is our formula for water potential, which helps us understand how water moves into or out of cells. In particular, we use this to study plant cells because they have a positive pressure. When enough water enters the cell, the expanding vacuole places internal pressure on the cell due to the cell wall, and that change in pressure can affect how water moves in and out of a cell. So now, in addition to solute, we also need to look at how pressure can influence the movement of water into and out of a cell. This is our formula for water potential. You have the trident. Trident P is pressure potential and trident S is solute potential. Note here that the water potential of pure water is always going to be 0 because in an open container there's no pressure and of course there's no solute. So 0 is the water potential of pure water. For animal cells, keep in mind you also will have 0 pressure because there's no cell wall. Water flows from an area of high water potential to an area of lower water potential. Most of the time these numbers are going to be negative, and that's something to remember when you're calculating your numbers. It's kind of human nature to look at a larger number and think that it's larger, but remember, if that number is negative, the larger a number when it's negative, the lower it is. For example, -8 is smaller than -2. Okay, now coming up, this is our first practice question here. This is the easiest question that I can ask you about water potential. If the cell's water potential is -2.5 and the solution that it's suspended in is -0.5, water is going to flow into the cell from -0.5 to -2.5. This is going to continue until dynamic equilibrium is reached. Or in the case of our animal cells, sometimes the cell may burst. Sometimes equilibrium may not be reached before the cell bursts. Again, this is prevented from happening in our plant cells because of the cell wall. I failed to mention earlier that the water potential and the solute potential formulas are on your blue formula sheet. You can look at those formulas now. Because the formula for solute potential is negative, it's negative ICRT, that C being your solute measurement. Because of that, as you add more solutes, the solute potential becomes more negative. And this makes sense because you know that water is going to move towards a solution where the solute is stronger. Okay, again, it's important to remember for our pressure potential in an open container or in an animal cell, due to the lack of the cell wall, the pressure potential is going to be 0. It won't always be directly given to you in the problem, but you can find it if you know that an open container will be 0. We learned these terms, turgid, flaccid, in class on Friday. As a plant becomes turgid, you can see there as the vacuole fills up, that's going to exert a positive pressure on the cell wall that we have to account for in our water potential problems. Okay, here is our solute potential formula. You've got the ionization constant, which we'll discuss in just a minute, molar concentration, pressure constant, and temperature. For this equation, the one thing I want to point out to you, the biggest mistake I see is that people multiply, they do all their multiplication and they forget to make the solute potential negative. So you need to come up with a way to help you remember to always put your negative. You can either make your ionization constant negative when you multiply, or when you write out like solute potential equals, like I'm doing here. Okay, you can just go ahead and put a negative there before you do any multiplication, before you solve for anything. Write your negative so that you don't forget it. Let's begin by talking about each part of the solute potential equation. The ionization constant is how the molecule will dissociate in water. So for all of our organic molecules, remember that they are covalently bonded. So those are all going to be 1. If you get sucrose or glucose or fructose, your ionization constant is going to be 1. The big ionic bond that you need to know is salt. We will see salt a lot. NaCl. It's going to dissociate into 2 sodium and chloride, 2 ions. For this example, magnesium chloride, your answer is 3. That's going to break apart into 1 magnesium ion and 2 chloride ions. But again, usually that'll either be explained to you, given to you that it ionizes, or it will be salt, which you should know. Salt dissociates into 2. C is for our molar concentration. That will be given to you. You will not have to calculate it. What you're supposed to get from this picture is that it's not about sheer volume, it's about concentration. So your small beaker and your big beaker here have the same amount of solute, but your small beaker is more concentrated because there's less water. It's the same amount of solute, but there's less water in your smaller beaker. That's what moles is a measure of. Okay, moles of solute per volume. And that number will be given to you. Again, it's a measurement of molarity. Coming up next is the pressure constant. Your pressure constant is always going to be 0.0831, and you can also find that on your formula sheet. Temperature, we need to convert to Kelvin. You're almost always going to be given your measurements in Celsius. You convert by adding 273 to your Celsius measurement. Here is our first example. If a cell's pressure potential is 3 and the solute is negative 4.5, what's the resulting water potential? And here, because both your values are given to you, all you're going to do is add those two together. Okay, 3 plus negative 4.5. And here I actually write my symbol wrong here. This is not the pressure potential, negative 1.5. Negative 1.5 is your total water potential here. And it's almost never going to be as simple as just calculating your water potential. You need to be able to determine if water is going to flow into or out of your cell. And what I strongly suggest you do is draw a picture. If you draw a picture, I feel like you're more likely to get it right. So what I'm doing here is sketching out my beaker, and then inside my beaker I'm going to draw my cell. The inside of my cell is negative 1.5, and the solution surrounding my cell is negative 4. Negative 4 is smaller than negative 1.5, and so water is going to flow out of this cell. And if you're following along on the paper handout, this is number 2 on your practice sheet. So water is going to flow out of the cell. Now, here's a more difficult question where we are asked to find the water potential and we're given our molarity and the temperature, but that's it. So we're going to have to find on our own the pressure potential and the solute potential. I strongly suggest that you guys start by taking an inventory of the information that has been given to you. So the first thing to note here is that it's given to you that this is an open container. So what that means for our pressure potential is it's going to be 0. Open container, 0 pressure potential. Okay, now we need to go about calculating our solute potential. So I like to write out every little thing. I like to inventory everything I have. So I'm going to make a note down here. I need to find my solute potential. I'm going to go ahead and write my negative so that I can remember that the solute potential that I calculate needs to be negative. All right, I'm going to come over to the left of this and I'm going to write out all the parts of solute potential. So So in order to find my solute potential, I'm going to need my I, my ionization constant. This is sucrose, an organic molecule. It's covalently bonded, so my ionization constant is 1. My concentration is coming from right there in the problem. It's 0.1 molarity. Remember, your R is always going to be the same, 0.0831. And then for my temperature, it's 20 degrees, but I need to add 273 to that. So my temperature is going to be 293. So now all I have left to do to calculate my solute potential is to multiply all these numbers together. I'm going to do 1 times 0.1 times 0.0831 times 293. And the number I get is negative 2.4. Your solute concentration, I can't think of any situation where your solute concentration is going to be positive. So that'll be one clue to you that maybe you've got the wrong answer if you get a positive number. Okay, I'm going to add together my pressure potential and my solute potential, which is already done here, and it's going to be negative 2.4 bars. Again, it's the same as my solute in this case because my pressure potential was 0. This is a U-shaped tube. What you're supposed to see here is the direction that the water would rise. This would have been better at the beginning of the PowerPoint, but honestly, I just forgot to move it. So if you're looking at this, you have more solution on the right side. Okay, I'm labeling them side A and B here for you. Okay, think about which way do you predict that the water is going to move. Is it going to move A to B or B to A? Okay, and you can see here it's going to move from side A to side B because water is going to move towards the higher concentration of solute. Okay, the water is going to decrease on side A and increase on side B. Okay, and as a result of that movement, I'm going to have osmotic pressure that I've labeled here. Now, I can reverse the direction in spite of the solute concentration by adding pressure here. If I add pressure, I'm going to reverse the flow to the other side. So the point of this is to point out to you that pressure does play a role in water potential and in the movement of water. So like in a plant cell, once the vacuole becomes very full, a positive pressure is going to be exerted on the cell, and it can cause water to move in the opposite direction if it's strong enough. So we finished this little presentation, and then we went through and we worked out the problems on the handout that I've also attached and sent to you. Questions 1, 2, and 3 are actually from the PowerPoint. 1 and 2 are from the PowerPoint. We skipped 3 because it's kind of out of scope. You're never going to be asked to convert from megapascals to bars, even though it's given to you there. So we started out on number 4. Okay, that's the value of our root tissue is negative 3.3. If we put it in a 0.1 molar solution at 20, what is the water potential of the solution and in which direction will water flow? Well, this water potential is actually what we just calculated on our PowerPoint. So that should look familiar to you. Again, my suggestion to you is that you draw out a picture. Our solution is unknown and our root cells are negative 3.3. So I'm going to start by setting that up, and I've drawn a question mark here because my solution is unknown at this point. So again, the water potential of this beaker is actually a question that we just calculated on the PowerPoint, so it should look familiar. But again, just to reiterate, my pressure potential is 0 because it's an open container, and then I'm going to use those values that I've been given, the 0.1 molar and the 20 Celsius to calculate my solute potential. So here again, I'm writing my solute potential equals the negative so that I don't forget to make it negative, and then I'm going to plug in all those numbers that were given to me. So multiply that together to get your water potential. okay, or solute potential, excuse me, and then add that to the pressure potential, which is 0. So my water potential is negative 2.4, and water is going to flow into the root cells because the root cells have a lower water potential. Negative 3.3 is smaller than negative 2.4. Now take a look at this second part of the question. I'm labeling it part B, and it's asking you if you had NaCl instead of sucrose, would this change the direction of water flow? In which direction would the net flow of water be? And what I want to encourage you to do is be smart when you get questions like this. You don't need to calculate the entire water potential over again. The only thing that's changing is your ionization constant. Your ionization constant is now doubled, which means your solute concentration will also double. Instead of being negative 2.4, okay, it's going to be negative 4.8. And this is going to change the direction of water flow. Negative 4.8 is smaller than negative 3.3. Water will flow out of the root cells. So salt water is much more dehydrating than sucrose solution because it does it does ionize in water, and so it has a stronger dehydration. Water is going to flow out of the root tissue, and this is one of the reasons that storm surges and hurricanes can be a real problem in coastal areas, because once it floods crops, there's a real dehydrating effect on those crops. Okay, now we have a more advanced question. A plant cell with a solute potential of negative 7.5 bars keeps a constant volume, that's important, when immersed in an open beaker solution with a solute potential of negative 4. What is the cell's pressure potential? That keeps a constant volume is important because it tells you what you need to do. If there's a constant volume in the plant cell, that means there's no net movement of water. The water potential of the plant cell is equal to the water potential of the beaker. And again, the way I know that is because if there's no water flowing, that means that the water potential is equal. Still, even when you know you need to do that, it's important to take inventory of what's been given to you and what you need to find. This particular problem is a little bit easier. There's no extra solving to do. For my cell, what's unknown is my pressure potential. I know that it's unknown because that's what the question is asking for. My solute potential for the cell has been given to me. The solute potential is negative 7.5 bars. Now, for my beaker is an open container. That's helpful to know, and I've also been given my solute potential. So the pressure potential is 0 because it's an open beaker, and my solute potential is given. It's negative 4 bars. Okay, and I've come down here to the bottom so that I have more space. I'm setting these equal to each other. Okay, the pressure potential is my unknown. So pressure potential plus negative 7.5 is equal to negative 4, the water potential of my beaker. I'm just going to add the 0.75 to each side. I'm going to add the negative 7.5 to each side. Okay, and that is going to leave me with the pressure potential of my plant cell. It's going to be 3.5. And notice that number is positive. It's going to be a positive number. Your pressure exerted on the plant cell should always be a positive number. Moving on to question 6. Question 6 is going to be set up the same way, but it's a more advanced problem because, as you can see, you've not been given your solute potential. It's worded a little bit different. Here it tells you the cell containing 0.6 molar glucose is in equilibrium with its surroundings. That's the same as saying the water potentials are going to be equal to each other. Again, I strongly recommend doing an inventory, writing down all the information that's been given to you and everything that you're going to need to find. So for number 6 and 7, they worked out the questions on their own, and then I checked their answers. I would like you guys to do the same thing. Complete 6 and 7. Shoot me a remind message or a Schoology message with your answers, and I'll get back to you on whether or not that's correct. If it's wrong, then what I'm going to do is I'll come through and I'll write out the solution for you so that you know what you need to do to solve it. Thanks, ladies.